So the assignment is to plot a graph, a titration curve, given the following information below. And essentially what you're going to do is you're going to plot and figure out these 5 points from the given information of a titration of a weak acid with a strong base. And from those 5 points, we should be able to fill in and sketch a titration curve. And if you can follow through all of these 5 basic points and get these points with all the calculations that support them, you pretty much understand everything you need to know in titration curves, at least weak acid, strong base. So let's get started. So very simply, the first thing I want to do in any curve, whether I'm reading one like we do in lab or calculating for one, is find my equivalence point. All right, so what do I have here? I have my weak acid and I have my strong base. And what I know here is that I have 25 milliliters of this acid. So I think about having some sort of beaker and having 25 milliliters of that acid. So that's going to be the volume in that beaker that I'm basically going to be dropping hydroxides into, where this weak acid, we'll just write HA, is here. Now, the bottom line here is I need to figure out the equivalence point. So I need to figure out moles. So the first thing I'm going to do is figure out the moles of both the acid and the base. So I have 0.25 or at least 0.025 milliliters of 0.1 molar acid. So the first thing that I'm going to do is I'm going to find the moles of acid in the beaker. So I have 0.025 liters, right? I went right to liters, not going to mess around. And I was given that the molarity of the acid was 0.1 molar, okay? And what do I know right away is that I know that acid, I know that the volume times the concentration is going to give me the moles of my H plus, my weak acid. And why do I want that? Because I know that's going to equal the moles of my base. So when I do this calculation and I times essentially 0.025 times by 0.1, I get the value for the moles to be 0.0025 moles, and that's of my acid, and that has to equal 0.0025 moles of my hydroxide. That's really important, okay, that you understand that. That would definitely be a point there. And knowing that it's 0.0025 moles of my hydroxide, which is going to be matched in this titration, right? The hydroxide from the strong base is going to basically stoichiometrically match up with the H plus. This is pure stoichiometry here, 1-to-1 ratio. Well, what do I know is, well, I know molarity is equal to moles over liter, and I have the moles. Okay, so the mole is 0.0025, and I know the molarity. The molarity of my solution, okay, that was given to me is 0.05 molar. So we're going to solve for the liters. What is the volume that it takes for me to add, don't forget what we're doing, to add certain amount of base into the acid. So how much volume do we need so that I have the right number of moles of hydroxide given the molarity? So essentially what we're doing is we're solving for L. And so when you do that, okay, and you solve for L, or the volume that you need of the base at equivalence, and all I'm doing algebraically is 0.0025 divided by 0.05 to solve for L, or the liters algebraically. And so when I do that, I get 0.050. So essentially 0.0025 divided by 0.05, and I get 0.05 liters. Or same thing is 50 milliliters. And what does that tell me, party people? Right away from just starting, and that to me is the first part here, is find the equivalence point, because everything else falls in place. All right, so right away I know that 50 milliliters is my equivalence point. So I know on this line, I'm going to have an equivalence point. And I'm just going to write a dotted lines all the way up to remind myself that that's where the equivalence point is. That's where the hydroxides equal the H pluses. And that's important. That's when I had enough of the base, enough of the moles of the hydroxide that were added that now matched all the what? All the acid. Now you say, well, H plus are acid. This is a weak acid. We have to remember, adding strong base is going to drive this reaction forward. Okay, and it's really important to know that just as much base is needed to drive all of this forward to neutralization. We'll talk more about that. But right now, because I know I need 50 milliliters to completely drive it forward, then right away I know I need 25 milliliters to halfway drive it. Now you say halfway drive it, what do you mean? Well, what I mean is I found my half equivalence point, or better yet, max buffering position, the place where I'm going to have equal amounts of what? Equal amounts of acid and base. Now, some people don't understand what I'm talking about here. This is the half equivalence point. This is where I have same amount of conjugate acid as conjugate base. Now, I want to write this so you can see what I'm talking about. We're going to get rid of this. But here's the reaction. We have HC2, and this is vinegar, okay, as we say in the rest of the world. And we're going to add the hydroxide, which is the strong base, and it's going to drive the reaction, no equilibrium here, to make water, who cares, okay, plus the conjugate base, C2H3O2 negative. Now, let's do a kind of a mole table here. All right, and I'm just going to put this in. We don't need to do this, but I'm trying to show you because people get lost in the sauce. What I need to understand is that I need, okay, to make equal amounts of the conjugate base and the conjugate acid. Okay, I have to halfway titrate this. Now, the equivalence point that we just calculated was all the way driven. Okay, so let me just pretend, let's just show you what this means. So let's just give it, so we had 0.025 moles initially. I'm just going to write this here. Okay, it's 0.00, okay? And when we add 0.0025 moles of hydroxide, okay, this was 0 and 0. Okay, of course, they both are going to go minus 0.0025 minus 0.0025. This would be what? Plus 0.0025, right? It's a one-to-one. These would go to 0. These would go to 0. This is going to be, we're not going to worry about the water. And this is going to be, of course, 0.0025. What does that mean? That means at equivalence, when we've added enough hydroxide to match the weak base and drive it forward, we're going to have 0 of both. And at equivalence, and this is going to be important when we come back to point number 4, we're going to understand that we now have 0.0025 moles of the conjugate base left. Now, what I want to show you is, well, wait a minute, let's just get rid of this for a second. What if we're halfway titrated? So we still have 0.0025 moles. Okay, we still start this way, but now we're going to add 25 milliliters of the hydroxide, which will give me half of the volume. So if I take in my handy dandy calculator, and it's really important you understand this, if I take 0.0025 and I divide by 2, what that's going to give me is, by dropping 25 milliliters of this what? Base, which we calculate will be the half titration point because we solve for 50, the amount of hydroxide I'd be adding would be half as much, so 0.00125. Okay, don't forget, and I'll just clean this up so we can see, the original amount of moles in my beaker, which is the acid, okay, is 0.0025. So we can see that by cutting this number in half, okay, I've got a much smaller number here. Now, this is driving it forward, and this would be the limiting reagent. We go 0.00125. This would be plus 0.00125, and this would be minus 0.00125. And if you can see that, well, this would be 0, and this is the halfway number, so when you subtract it, you get 0.00125, and this you're adding to 0, 0.00125. And what do we see, party people? When I have this number, okay, which represents half the volume I added at 25, this is the moles that I'm adding. And when I drive it forward, I'm going to wind up having the same amount of conjugate base as conjugate acid. When I drive it halfway, that means half of the acid became the conjugate base and half is remaining. And then there's the scenario where the conjugate base and the conjugate acid have the same moles. And that's important because if I want to do point 2 and find this pH, halfway equivalence point, if the moles of the conjugate acid and conjugate base are the same, something really important comes by, and that's the Henderson-Hasselbalch. The pH in which you have this is equal to the pKa, okay, plus the log of the conjugate base over the conjugate acid. Now, because the conjugate acid and the conjugate base have the same volume and they're in the same container, okay, I can put the moles in here. And usually it's concentration that we put in here, but we can put the moles because they are in the same volume here. The liters would cancel. Okay, so we are allowed to do that, but if you're never quite sure, you can put the concentrations in. So I'm going to put the conjugate base, which is 0.00125 and 0.00125. And what do we know? The log of these numbers will be 1. And the log of 1, as we talked about before, is 0. And what do we know, party people? pH equals the pKa. What is the Ka of this acid? Well, it was given to you. It's 1.8 times 10 to the negative 5. So what you're going to do is you're going to take that Ka and do a negative log. And when you do the negative log of that Ka, you get a pKa of 4.7. So the pH equals 4.7. All right, so the negative log of this is 4.7. What does that tell me? At the half equivalence point, okay, which we just figured out, these guys are going to be in the same value. We drove it halfway. That means we have half as much, or we'll have the same amount of conjugate base as conjugate acid because half of the acid became the conjugate base and half of it remains. And that position, pH equals pKa. So at 4.7, right here is my first point. This is number 2. Okay, we needed the volume to know that. So here we go. Now let's go after, as my voice is breaking up, the initial pH, this point here. And how do I do that? You notice everything we've just did so far was pure stoichiometry. How many moles compared to moles? Because a weak acid needs to be driven by a strong base. But this is important. What is the concentration of the acid just sitting in the beaker? Well, it's reacting with water, and when it does so, it's going to be in equilibrium with its reverse reaction. So let's clear some space here and talk about how do we figure this out. Well, this will be an equilibrium problem. It's a weak acid, so it doesn't completely dissociate. So let's go do it. All right, so let's write the reaction. It's going to be HC2, H3, O2, and it's just sitting in water, so water is the predominant species it reacts with. It's a weak acid, so it's going to basically protonate water a little bit. Water becomes H3O+, which is synonymous with protons, and then what's remaining, of course, is the conjugate base, C2H3O2 negative. Okay, so initially, okay, what's my concentration? Well, the concentration of my acid is 0.1. And that's my initial. These guys are going to be 0. Okay, well, this is going to go down. This is 0.0, or I should say, it's going to go minus x. This is going to be plus the same x because it's a 1-to-1 relationship. And of course, so that's a change. At equilibrium, we're going to have 0.10 minus x. And of course, x plus 0 is x. It's the same of them. And so what we have left is we have our formula. And it's going to be the Ka, which we know is what? 1.8 times 10 to the negative 5 is equal to the products over reactants, coefficients become exponents, solids and liquids don't apply. So it's going to be the concentration of the H3O plus times the concentration, they're both X. So that becomes X squared. All over the reactant, this is a liquid, so we don't consider, but this is aqueous, and this is zero point 0.1 minus X to stay away from the catastrophe of the quadratic catastrophe. We approximate that away for reasons we've talked about previously, and now we can solve for x. So times this by 10, do the square root of both sides, and when you do that, you get an x that is equal to 0.00134. And what did I just solve for? I solved for the H3O plus concentration. What are we trying to do? We're trying to find the initial pH, or the initial point, 0.1. Well, at 0.1 there's 0 volume, so we just need the pH. So if I have the H3O plus concentration with the acid sitting in water, all I have to do is negative log this. So the negative log of this concentration, which is H3O plus, gives me 2.9. So my pH is 2.9, and that's my first point. So 2.9 right there. Okay, so the pH 2.9 right there. And so I have my first 2 points done. That's point 1. This is number 1. And we have half of point 3, meaning we know the volume, but we do not know what the pH is. And this is the one that requires the most work. So I am going to get rid of some stuff here, and we're going to go after what the pH is at equivalence. Now I will say, party people, that if we had a strong acid, strong base titration, this would be an easy answer. The pH would be 7. But because we have a weak acid, and weak acids have a very small Ka, which means their conjugate base has a larger value, the conjugate base can ionize water. So let's talk about this reaction again. And there's a little bit of work here, but you should be able to follow it. So back to this reaction again. So HC2H3O2. Okay, now this is a scenario where we've just reached equilibrium. Okay, so let's talk about now if it just reached equilibrium, and let's talk about what happened with the hydroxide. It drove the reaction to become the conjugate base C2H3O2 negative, and of course this conjugate base, this base hydroxide strong base, pulled the H off to make water. So when we drove the reaction completely this way by adding just the right number of hydroxides to match the H's or the acid, we have 100% conjugate base. We've talked about this before, just before. So when I had, forget this number, 0.0025, what do we know? Well, it's going to be minus 0.0025 all the way across, and plus 0.025 all the way across. And when that happens, minus 0.0025 minus 0.0025 plus 0.0025, okay, what you're going to have is 0 for both of these, but you're going to have 0.0025 moles of this conjugate base standing, and these guys are all gone to 0. They've all been used up, and you have 100% at the what? Equivalence point. So you need to understand that C2 H3, the conjugate base O2 negative, is now just sitting where? In water. Okay? And what's it going to do? Well, it's a base. It's a weak base. It's not a very strong base, but it has an ability to yank H's off. And what does it do? It reforms the acid HC2H3O2 negative. No more negative, sorry. It reforms the acid, and by pulling an H away, it makes a hydroxide. What did it do? It created hydroxides. This weak conjugate base which was the conjugate base of the weak acid, has an ability to yank H's off water and ionize them into hydroxides. So that means that with a weak acid, you have a relatively strong conjugate base. It can pull H's off, which means it's going to create a basic scenario at equivalence, which means we should be above 7. But again, we need to solve for what this concentration is, and then we can get pH. So guess what? It's an equilibrium problem. So let's get after it. So how much of C2H3O2 do we have? Well, we figured out it's 0.0025. Now these are moles. Now we do equilibrium problem with molarities. So this is moles. And the question is, okay, if we're trying to get molarities because we're doing an equilibrium problem, what is the total volume? Well, at the equivalence point, as we just figured out a little while ago, we have 50 milliliters here of base that was added. Added to what? It was added to 25 milliliters of acid here. So I've got a total of 75 milliliters, because at the equivalence point, we're talking about 50 milliliters of base being added to the 25 milliliters of this beaker already. So there's a total volume sitting in the beaker of 75. You have to realize that. So we're going to go find the molarity. 0.0025 over 0.075 liters gives me a molarity to be 0.0333. Okay, so I'm going to get rid of that. So I had to take the total moles and I divided by 0.075, and it gives me 0.0333. So that's my molarity. So let's go after the question here. So initially, we have 0.0333 molar. We have 0 and 0. We always assume it's all together. That's the initial. The change is we're going to lose something. This is going to gain. And of course, at equilibrium, 0.00333 minus x. And some of you guys can write this already without this, and I get it. I'm just showing others. So bottom line is you're going to come up with the equilibrium constant equal to x squared over, we're going to approximate away this x. This number is very big compared to that x, so 0.0333. Okay, now you say, okay, K, but it's not the Ka, it's the Kb. This is a base. This is the opposite reaction, right? Don't get lost in the sauce here. We drove this reaction forward, and now we have this conjugate base sitting in water. Well, it's going to do the opposite reaction. So we have to find the Kb. Well, we know the Ka, and we know that Ka times Kb is 10 to the negative 14, which is Kw, the equilibrium constant for water. So when we solve for Kb, Kb is equal to 10 to the negative 14 over the Ka, which we've used already, given to you in these problems, is 1.8 times 10 to the negative 5, 1.8 times 10 to the negative 5. And so when you do that, okay, you get 5.56 times 10 to the negative 10, and that's my Kb. So 5.56 times 10 to the negative 10 equals x squared over 0.0333. So I times the 0.033 by my Kb and square root both sides. Okay, and when I do that, I find that my x is equal to 4.30 times 10 to the negative 6er. Okay, now what did I just solve for? Well, I just solved for the x, which is the concentration of my base. Okay, now what do I do with that? Well, I am going to find the negative log of that. Why? Because that will give me my POH. So negative log of this number, and put in my handy dandy calculator, I get a POH, little p means negative log, of the hydroxide concentration to be 5.4. Awesome. But I want the pH. So I subtract it from 14. So 14 minus 5.4. And what I get there is an 8.6 pH. And what I just found, party people, was the pH at equivalence. Okay? And so this dotted line of 50 milliliters that we found earlier, now we can put a dot there. Okay, I'm going to clean up some things to get it out of my way so my dot can be relatively permanent. So I know that at 8.6, okay, right around here, that's my equivalence point. I know it's at 50. We did the earlier work to figure out how much moles of hydroxide is needed and what that volume was. And now we figure it out by understanding that we're going to have a 100% conjugate base at this point. So the moles of the hydroxide eventually become the total moles of the conjugate base. We understand it's sitting in water now, and it has some ability to ionize water because a weak acid is a pretty strong conjugate base, so it'll pull the H's off. And so we do an equilibrium problem. There's no more stoichiometry here because there's no hydroxide anymore to drive it forward. So I did a equilibrium problem. I realized that the reaction is the reverse of Ka, so Kb, and I had to calculate it, solve for X, found that it was a hydroxide, did the negative log to find the POH, subtract from 14, and I got my pH here to be 8.6. And that is point number 3. I'm sorry, point number 4. Okay, we're getting there, but I jumped the gun. All right. Cool. All right. So let's go on to the last point, which I think is probably the easiest point that we've already done before. And I said to you that we're ending this at 70. So it's 70 milliliters. The question is, where do we go? So let's get rid of some of the things we have in the way here. And let's go find the 5th point, which would be the final pH. Okay. All right, so I'm going to get rid of this. Okay, and let's do this. Now, the final pH, same idea, except now, once we're past equivalence, there's no more hydroxides. But if I keep adding hydroxides to the 70 line, and let's just make sure I know where the 70 line is. If I keep adding OH minus drops of base or milliliters of base to my beaker after what? After equivalence has been reached, then what I'm doing is I'm adding excess hydroxide. So this is just extra hydroxide on top of a what? Neutralized solution. So my pH at 70, and again, we know it's 70 because I said that's where we're ending. What's my pH to write this final point? Is basically nothing more than the concentration of the hydroxides, right? And if I know the concentration of the hydroxides at this 70 milliliter mark of the titration, negative log, just like we did before, that'll give me my POH, and then subtract from 14, and I get my pH. And I can put that there. But so what's the concentration? Well, how much volume am I adding of extra base from 50 to 70, right? This is 70, this is 50. So we have 20 milliliters of extra. So let's go find the moles. We've done this before. So 0.20 liter. What was the concentration of the base? I believe that was 0.05. Just make sure I check. My short-term memory is gone at this height. 0.05 liters. Okay, so when we do that, we get a total moles, okay, to be, we get 0.001 moles of extra hydroxide. And we want the molarity, right? We want the concentration, right? That's how we get a pH from concentration. So we're going to divide by the volume. And this is tricky. Do not divide by 70. This is 70 milliliters of base added into a beaker that already had what? Already had 25 milliliters. So we're adding the 70, okay, with the 25. So the total volume is 95 milliliters. So we're going to divide this by 0.095. So when you divide with your handy dandy calculator 0.01 by 0.095, okay, what you get is a concentration, okay, equal to 0.0105. That's the concentration of my hydroxide. And just as we said, let's do negative log of that. Negative log. Second answer. Okay, I get 1.97. All right, and then I'm going to minus that, or 14 minus that, and essentially I get 12.0. Okay, so I found the concentration, did the negative log of this, and I got 1.97 or 98, and basically that's equal to my POH, as we talked about. 14 minus this number is 12.02, so 12.0. So we found the pH. So at 70, my final point, okay, my final point is about 12.0. So really it's important to realize the final pH of your titrations, if you go past the neutralization point or the equivalence point, is just due to the extra, in this case, hydroxide that I added. And knowing the new total volume, okay, I was able to do that. All right, very, very simple. And now the last one, so this was number 5. So we have our 4 points. We have one more left. And I asked you to give me the point, okay, at 40 milliliters. So right here, what's the, so we know at 40 milliliters, we need to know what the pH will be when I added 40 milliliters. Okay, now this is a buffer region. Okay, I'm a little past max buffering position. So to answer this, we're going to use the Henderson-Hasselbalch equation. All right, so I am going to clear some area here. And what we're going to do is we're going to, now we could do this problem with an equilibrium problem, but it's so much easier to use Henderson-Hasselbalch. We've used it once before to find the pH at the halfway equivalence point or max buffering position, but let's write it here. So pH is equal to the pKa plus the log of the conjugate base over the conjugate acid. Okay, so I want to find that pH. Well, I know my pKa. My pKa that we found is from our graph is 4.7, and you can just take your Ka, which is 1 point, what do I have here? 1.8 times 10 to the negative 5, and all you do here is do a negative log. Little p means negative log, so pK is the negative log of this, and what you get is 4.7. So this is a 4.7. Now the question is, what is all this? Well, I didn't erase this point because I want you to see what's going on here. The question is, how much of the acid and base do I have? They're not going to be equal. So let's get rid of some things here. All right, so what do we have? Well, we know initially that we have 0.025. And I want to get rid of that crisscrossy mess that I have here. We know that we initially have 0.0025 molar. That doesn't change because, and I'll just get back there. That doesn't change because that's what still was in the beaker. Okay, so this is O2. So the question is, how much hydroxide did I use? Well, if it's 40 milliliters, 0.04, right? 0.040, it's liters. I'm going to times by, this should sound familiar, by my concentration, which was 0.05, just make sure. I've been doing a couple of different problems today. 0.05. So I'm going to times this together. So taking my handy dandy calculator, I'm going to find the moles of the hydroxide, strong base, that was added after 40 milliliters. So 0.04 times 0.05, and I get 0.002 moles. So 0.002 moles. Remember, this is a mole table. I'm doing stoichiometry here because I want to see how far I drive it. I need to know how much of the conjugate acid and conjugate base are remaining at that point. And because we're using hydroxides, we're driving it forward. These guys are 0, and I'm not in love with the blue right now. So we're going to minus 0.002. Okay, and when you do that, you get 0.0005. That's at the end of the reaction, or at that point. This is minus 0.002. This is plus 0.002. At the end, I have 0.002. Okay, so you can see at this point, by adding 40 milliliters of this base with this concentration, that's how many moles of hydroxide I've added. And it's going to drive this weak acid forward, not to completion, which would be right here at the equivalence point, but a partial way, not halfway. So the important thing is I have some moles of my conjugate acid and I have my moles of the conjugate base. I'm going to put them right into my Henderson-Hasse block. Like I said, I can do that with moles because essentially I'm dividing them by the same volume. So this is 0.002 for the acid. I'm sorry, the conjugate base on top, and this would be the conjugate acid. And you can see there's a smaller number. This is a smaller number for the acid than the base. The base is bigger, and that kind of makes sense that our pH should be a little bit higher. So essentially what I'm going to do is find the log of 0.002 over 0.0005. So you do that in your handy dandy calculator, 0.002, and divide by 0.0005. And when you do that, you get, okay, let's do that again. I'm sorry, so when you have 0.002 divided by 0.005, you're going to get 4. And so what you do is you do the log of 4, which is 0.602. So 0.602 is the log of that ratio, which is 4, and I'm adding it to 4.7. And when you do that, you get approximately 5.3, and that's my what? pH, with that ratio of conjugate base and acid available. And that's my last point. So at 40, I need 5.3. And no, 5.3 is about right here. And so I go across, and that's my third point, but my final point. And hopefully I made enough good points in this lab so that you understand it. Yes, I was going there. Now you should connect the dots, okay? So to connect our dots, and I know I got stuff everywhere, we'll make this a relatively thick line, and let's have a fun color here. How about we do pink? Yeah, let's go. I should do white, right? I'm gonna do green. Here we go. So let's make it pretty thick here. And so you're gonna come up, try level off somehow. You're gonna asymptotically come up, and then you're gonna try to level off, trying to go to the concentration. All right, so that's good enough for me. I hope that helped. And again, go through it. I actually have another example with a key, and good luck.